Welcome to lecture 2 of this week. We had done a brief review of what we had done in the previous 2 weeks, and we are poised to look at what the atom looks like. The structure of the atom really starts, the story of the structure really starts in 1911 with Lord Rutherford. So Lord Rutherford in 1911 did a pioneering experiment. The experiment basically involved probing the atom using small objects, and those objects in this case were alpha rays. At that time nobody knew what an alpha ray was, except that they were found in radiation. So you had certain radioactive substances like uranium, radium, which emitted alpha rays and beta rays. People didn't know what they were, but people would soon find out the next decade. For our purpose, it is very it's only imperative to know that alpha rays are just positively charged particles which travel at quite high speeds. So Lord Rutherford used a high energy beam, an alpha particle, which was used to probe the atom, and these alpha particles were directed at a gold foil. Okay, so here is what atomic here is what the experimental apparatus look like. There is a source of alpha particles right inside this lead container, and the lead container prevents the alpha particles from moving out in other directions. There is a small hole right in the middle in the front, and the alpha particles move through that hole and strike this gold foil. The gold foil is exceedingly thin, and note the apparatus. Here you have a detector all around, and this detector is just shown in one strip, but the detector is really all encompassing. It's like a sphere with a small slit in front. And these alpha particles come from a source, and the source is radium. So it had a small amount of radium inside a lead container, and the gold foil was exceedingly thick. And the thickness of the gold foil is something around, like the average thickness is something like 8.6 10 to the minus 6 centimeters, which in modern calculations, now that we know the radius of the atom, it's something like 10, 20, 50 atoms thick. So it's an exceedingly thin film of gold. Okay? And the detector was zinc sulfide. So zinc sulfide has this property that when an alpha strikes zinc sulfide, there is a bright light, there's a scintillation. Okay, there's a bright glow, there's a spot, and you can count the spots. You can know at which place the alpha particle strikes and how many alpha particle strikes at what angle. Now coming to the observations. The observations are pretty nice. And so what did Lord Rutherford observe? Lord Rutherford observed that most of the alpha particles just went straight through. Okay? They're just going straight through like this, and once in a while some deflect, but through a small angle like this. Okay, so if this is the line which is going straight, there are small deflections. But once in a while, and this was a huge surprise, once in a while you have some which rebounded by 180 degrees. Basically it came back. So you have an alpha particle being fired, and these are small particles, but they're heavy and they are traveling fast, and they should go right through the gold foil, but once in a while they just come back by 180 degrees. And this surprised Lord Rutherford to no end, and he said it's as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. So obviously the gold foil was not merely a tissue paper, it just gives an appearance of a tissue paper. There was something heavy lurking. And then Rutherford came to the following conclusion. The conclusion was this: the atom is mostly empty, but there is a very heavy mass. In fact, most of the mass of the atom is there right at the center. So this is the central mass, and it's very dense and it's positive. These repel, remember, like charges repel, these repel the positive alpha particles and they just come back. So if these hit the nucleus, this part is called the nucleus, by the way, if this hit the nucleus head on, they just come back by 180 degrees. Most of the alpha particles just go through because most of it is empty space. The nucleus is surrounded by a cloud of electrons. So there are electrons which are orbiting the nucleus and something like a cloud, and if an alpha particle happens to go through the cloud, it just buzzes through. It It just sweeps the electron. The electrons are very, very light, just sweeps the electrons aside. But the nucleus is a whole different matter. You can't sweep the electron from the nucleus aside because the nucleus is very heavy. So it exchanges momentum and just comes back. It's like hitting a brick wall. So that is now the structure of the atom. The structure of the atom is a small, very dense nucleus occupying very little space, but it's very massive. It encompasses almost all the mass of the atom, and there are electrons which are surrounding it. So a brief recap of the experiment. So you have alpha particles being fired at the gold foil, and the scattering pattern reveals a dense positive center with small negative charges which are orbiting around it. The atom is then just the nucleus, which is the central positive charge, and there are electrons revolving around the orbit. However, nobody really knows how the atom functions in the physical sense, like what is the physics which governs such a system. For example, we have the Earth and the Sun system. Okay, Earth moves around the Sun. We know that gravity is responsible. We know that we can calculate things from gravity. We know that we know the force law for gravitation. Okay, do we know similar principles for the atom? At this point, no, we do not. And it turns out that the physics which governs the atom is very, very different from the physics which governs the Earth and the Sun and the Moon. So the Rutherford model was very simple. The Rutherford model basically said that there's a nucleus which consists of protons. The neutron was not discovered in 1911. It was discovered much later. It was discovered in 1932. So neutron was to come 21 years later. So Rutherford did not know about the neutron. So he said the nucleus is made completely out of protons. And so it's made up of protons, and there are electrons which move around in orbits around. So this is more or less the atomic model. So you have the nucleus and the electrons which are moving around it. The questions still remain. The question is, why is it that the atom is so stable? We don't know an answer to that. Okay. Furthermore, what is the underlying principle of the underlying physical principle which governs the atoms? What are the laws? Can we calculate anything? And these answers were partially answered. These questions were partially answered by Lord Rutherford's student himself. His name, Niels Bohr. This experiment happened in 1911, and Niels Bohr gave a model in its finality 1913, so 2 years later. And this would be the final triumph of the old quantum system, the old quantum mechanics. So Niels Bohr was the first person to realize that the atom is not that simple system. It's not a system which can be explained classically. You have to involve quantum mechanics in order to solve the atom. Okay, he was just building on the knowledge that was got from Max Planck and Rutherford, and Max Planck and Albert Einstein, and he says, okay, this Rutherford's model of the atom was okay, but I can refine it by using quantum mechanics. And so he gave a series of postulates. Okay, and these postulates are not supposed to be questions; he said they just are. So in 1913, we got some new postulates regarding the structure of the atom, and these postulates were the mishmash of quantum mechanics, the new quantum ideas, and the old classical ideas. So this is Niels Bohr, and what he did was he treated electrons as classical particles. So they follow classical trajectories and everything. We'll soon learn what we mean by classical trajectories and quantum trajectories. So they are classical particles. You have them moving in particular trajectories which you can trace and draw on a paper, and but the real difference between the electrons and other particles were that electrons, at least according to Niels Bohr, were classical particles, but they followed quantum mechanical rules. In other words, you had certain quantization conditions which were followed by the electrons. Okay, we'll soon realize that this is not an entirely correct statement, but in 1913 this was the first step that was taken. The first step is never completely correct, but it's a very healthy first step. So here come the postulates. The first postulate is that electrons revolve around the nucleus in only certain orbits. Okay, the Earth could have been a few kilometers, few thousand kilometers, nearer to the sun or farther away. but it turns out that electrons couldn't have been. The electrons revolve around the nucleus in only certain orbits, and these orbits are very, very specific orbits. You cannot have the orbits a few nanometers farther away or a few nanometers closer. At least in the Bohr model you cannot. And these orbits also have particular energy. So when the electron is in that orbit, it has to have that energy. So the electron cannot have any arbitrary energy inside the atom. So you have an atom which has a nucleus, and Bohr's model does not talk anything about the nucleus. It has a nucleus and it has one electron, and that electron can be in any of these orbits. There can be many orbits, but these orbits come at only discrete energies, and so energy is quantized. You can have E1 and E2. You cannot have E1 plus E2 by 2. You cannot have any energy between two energy levels, and this will become clearer in another minute. These orbits also possess only certain angular momentum. Remember, angular momentum is the momentum associated with a body which is rotating, which is revolving. So electrons are revolving bodies around the nucleus, so they have particular angular momentum. Okay, and it turns out that each of these orbits also have a particular angular momentum. Okay, so an electron cannot have any arbitrary angular momentum. So the electron cannot have an arbitrary energy, the electron cannot have an arbitrary angular momentum. Okay, so the angular momentum is also quantized. This is the first time anybody has talked about anything, any quantization besides energy. We talked about quantization of energy for Planck and for Einstein, but Niels Bohr said, okay, besides energy, there's another quantity which is quantized, which is the angular momentum. And a very important phenomena is the transition that an electron can make. The electron can make a transition from one state to another state. Okay, so it can make a transition from a state with certain energy, say E2, to another state with another energy E1. Okay, and if E1 is less than E2, so the electron jumps from a high energy state to low energy state, what happens is that the radiation that is emitted, okay, this radiation comes from the atom itself. The radiation which is emitted is equal to the difference between the energy levels of these two between these two levels. So you have some E initial and E final, and the difference between these two levels is what is emitted. Okay, this is very, very important. We'll see the importance of this in a minute. Okay, so let's see what this atomic model looks like. So here you have this is basically Rutherford's model. Here you have the nucleus, and you have the electron, and there are these certain orbits. Okay, so first Bohr's postulate, there are only certain orbits. If there are only certain orbits, we can label them using label, say n. The n can go from 1, 2, 3. So this is n equals to 1, this is n equals to 2, this is n equals to 3 and 4. Okay, we can't have anything other than these. We can't have n equals to 1.5. Okay, n is an integer. Now these orbits have a particular energy. Okay, now just like we label these orbits by n, we can label them by energy. Say the first orbit has energy E1, the second orbit is E2, third E3, and fourth E4. Okay, these are two equivalent ways of naming. Okay, you can either name it by n or by energy. Okay, we'll see the two are actually related, but that's not. We'll come to that in a minute. Okay. So we can use the energy as a label, and the electrons are in one of these orbits, and they're happily revolving. So let this electron revolve in E1, perfectly fine. There can be in E2 and move with an energy E2. The electron in energy orbit E2 will have an energy E2. Okay, or it can be in E3, and it has to have the energy E3, which is different from E1 and E2, and the electron can happily be there. Okay, very simplistic picture, very nice picture. But say you want something else. Okay, you don't like these orbits, you want something else. You want these are the orbits that I was talking about, n equals to 1 to 4, and you want the electron to be in the middle. Well, the Bohr model tells you that you cannot. There are no orbits which are permitted, so this is not possible. Okay, so the electron cannot be in an orbit which is in between two orbits, anywhere in between two orbits. So it can be in n1 or n2 or n3. It cannot be in 2.5. Okay, so this is gone. The orbits possess a certain angular momentum. We'll talk about angular momentum. It's a more complicated subject. We'll talk about angular momentum in a bit. Let's just concentrate on energy now. And the spectacular part of the Bohr's model is the transition that an electron can make. So say the electron is in the orbit E3, orbit with the energy E3. Okay, so the electron is here, and now it can make a transition. So it makes a transition and comes to E1. So it jumps from E3 to E1. We use this very loose languages, jumps from E3 to E1. Actually, it makes a transition from E3 to E1. It doesn't jump anywhere. It was there in E3, it comes to E1. Okay, and in doing so, it emits a photon. Okay, with the frequency nu. So the energy of the photon is h nu. And I told you that the radiation which is being emitted, the energy of the radiation will be the difference between these two energy levels. Okay, the difference between these energy levels will be, so the difference in the radiation will be the energies E3 minus the energy E1. So this is the difference. So this is the formula we had. This is delta E, which is just E3 minus E1, and h nu has to be equal to this. So this photon which is going out of the atom is equal to the difference in the energies. Okay. Now say you have a large number of photons which are coming out from the atom. Okay, and if you have a large number of photons which are coming out from the atom, it can happen from say the electron can make a transition from E3 to E1, like it's happening here, or E2 to E1, or E3 to E2, or E4 to E3, or E4 to E2, E4 to E1. All of these are valid. These are all valid transitions. Okay, they will give you a particular frequency. Okay, these frequencies can be noted on a spectrograph. You can know these frequencies, and these frequencies are nothing but the differences between energy levels. Multiplied by h, of course, but these frequencies correspond to the difference in the energy levels. So just by taking, say, hydrogen, okay, a few hydrogen atoms, a gas of hydrogen, and just heating them and see what radiation they give, okay, you can find out the difference between the energy levels. You can find out the spacing, the energy spacing inside the atom. That is extremely deep. You're measuring something which is very gross to measure. It's very simple to measure. Okay, it's a macroscopic property. It's a property for which you have a large machine. You don't need too much fine tuning. You can measure it very, very nicely. Spectroscopy is a very well established subject. But what you're gaining, the knowledge that you're gaining, is about the spacing inside the atom, which is extremely small, which cannot be seen. Okay, of course you do not know what E1 is. You do not know the energy of this orbit. Okay, but you can know the spacing, and once you know the energy of this orbit, you can find out the energies of all other orbits. It's beautiful. And so the Bohr model continue. We're going to talk about angular momentum now. So let me just tell you what angular momentum is. So it's associated with the revolving body. I've already told you that. Okay, it's the momentum which is associated with the revolving body, and if the electrons are revolving around the nucleus, it also has angular momentum, quite obviously. Okay, because it's a revolving body. Very simple. And the angular momentum for a body with mass m, okay, which is moving at velocity v and in a radius r, so it's moving in a circular manner. Okay, the radius of the circle is r and the velocity is v. The mass of the body is m. The angular momentum is simply given by mvr. Remember, the linear momentum is just given by m into v. So the angular momentum is given by mvr. Okay, it's moving in a circle. That's all that we need now. What Bohr said was that this quantity is quantized, which means that it comes in only particular values. Okay, what that means is that this L is actually some number n into h by 2 pi. H by 2 pi is a constant. H is the Planck's constant, and you can just divide a constant by 2 pi. 2 pi is being a constant. H by 2 pi is a constant. So n is an integer. It can be 1, 2, 3, and so on and so forth. We had seen this before as well. The energy came in quanta, which means that if you have a frequency nu, then the photon, each photon had an energy h nu. Okay, and now you can have one photon or two photons or three photons, and the energy would be h nu or 2h nu or 3h nu. So the energy would be n into h nu. Here the angular momentum is just n into h by 2 pi, and this is our new angular momentum. This is a completely ad hoc procedure. This is the completely ad hoc postulate rather, and Bohr did not know the answer to this. The answer would come much later, but this was a brilliant suggestion. Okay, it's brilliant because it worked really, but let's just see what it leads to. So if you combine this equation with this equation, you simply get this following equation. This is called the Bohr condition. The Bohr condition basically tells you that the angular momentum is quantized and mvr is equal to n into h by 2 pi. Okay, now this model is pretty nice, and it tells you a lot of things qualitatively. It explains a lot of things qualitatively, but does it explain anything quantitatively? Okay, can you calculate things? And it turns out that you can calculate lots of things. You can calculate the velocity, you can calculate the radius of the orbit, and you can calculate the energy of the individual orbits. Okay, so let's just go on calculating them. I won't show you the exact steps, but I'll just give you the numbers, and I'll show you something which is a brilliant prediction of the model. And the miracle of all of this is that these quantities, the velocity, okay, the radius of the orbit, the energy of the individual orbits, you might think that they would be horrendous figures, okay, horrendous numbers, but it turns out that it depends only on one single parameter, and that parameter is the label n. N can be 1 for the first orbit, 2 for the second orbit, 3 for the third orbit, and it depends only on this one integer parameter. The integer is integer decides what the velocity of a certain velocity of an electron in a certain orbit is. So this is the miracle, and let's just list out the quantities. So you have a single electron atom, okay, and the nucleus can have an atomic number Z. So this is like hydrogen atom, but the hydrogen atom is just one proton. You can have heavier nuclei. You can have the proton of helium or lithium or anything of that sort. You just have to substitute Z properly. So the nucleus might have 2 protons, so Z is 2, 3 protons, Z is 3, 10 protons, that is 10, and so on and so forth. But the number of electrons is only 1. Bohr model does not work for 2 electrons or 3 electron atoms. It just works for 1 electron atom. So it's a very good model for a hydrogen atom. So let's just kind of concentrate on the single electron atom, and you have these parameters to depend upon. The parameters are the mass of the electron, which is a very well measured quantity, the charge of the electron, again a well measured quantity, and the atomic number, Z being the atomic number. So we know the values of all these parameters. So the velocity of an electron in the nth orbit is just given by this expression. So this is the velocity of the electron in the nth orbit. It's given by 1 by n into a constant. Now this might look scary, but it's really not. It's just 2 pi z e square by h. All of these are constants. We know the value of 2 pi z e square and h. This is just a constant. This goes in a bracket like this. Okay, so it's 1 by n into some number. So the dependence, the only variable is really n. So the dependence is only 1 by n and nothing else. Okay, this is the velocity. The radius is simply this. The radius is n squared into another quantity. So this constant is again a constant. It's just a constant. It's just a number. So the radius goes as n squared. The velocity goes as 1 by n. Okay. These are just absolutely brilliant suggestions. So if there's a certain radius for the first orbit, the second orbit will be 4 times as large, because n square, it goes as n square. The second orbit 4 times as large. Third orbit will be 9 times as large. So the atom is really very, very large in volume. Okay, because the orbits are very, very widely spaced from one another. And let's calculate the all-important energy. And all-important energy again depends only on 1 by n, and you have a bunch of factors here, but then these are just constants again. You can calculate them once and for all and just keep on dividing by 1 by n squared. So En is just minus 1 by n squared, and there's a crucial negative sign here. The negative sign comes from the fact that the electron is an electromagnetic field. Okay, anything which is if the charge is opposite to, so the electromagnetic field is due to a positive charge. The nucleus is a positive charge. Okay, if you keep a particle which is negative, in a positive electromagnetic field, then the energy of that particle is negative. Okay, that's a standard procedure, standard convention that is followed in physics. um, so the energy is negative, and it depends on 1 by n squared, okay, into a certain constant. Okay, awesome. So now we're ready to do something. We're ready to calculate this constant, okay, minus the z square. We're just ready to calculate this constant, and we're ready to calculate this constant again. Okay, so we take a hydrogen atom, and for hydrogen atom, obviously the z is 1 in each of the cases, and E naught, it should actually be E1, which is the first orbit. E naught is just minus 13.6. So this whole thing with n put to 1, so this is E1 actually, not E naught, sorry for the mistake. N equals to 1, this whole thing with z equals to 1 is just 13.6. So this is minus sign here, so minus 13.6 eV. This eV is a new unit which you might not be familiar with. It's electron volts. We'll talk about these new units in a lecture or two. Don't bother too much about them. Just take it as some unit like meter, kilometer, joule, etc. Let's just say that the unit is just eV. Okay, so in some unit eV, the energy is given by minus 13.6. Okay, this is a figure, this is a number which you can commit to memory. The R1, it's not R0 again, it's just R1. Again, you put n equals to 1 and z equals to 1 here, and this whole quantity is just 0.53 angstrom. Angstrom is also another unit which we'll define in some time, okay, in our lecture or two. So so these are the two numbers which you will keep in mind. So this is the ground state energy of the hydrogen atom. This is the ground state radius of the hydrogen atom. Okay, so if there's an electron in the hydrogen atom, most of the time it will be inside the ground state, or in the ground state, and it will have an energy like this. It will be an orbit which has radius of 0.53 angstrom. Okay. Now for a Bohr atom, therefore, we just restore the z and the z square, and the z square comes here, and it's just 13.6 z square, and the n square comes back as an n square. Okay, and so this is the energy of the nth orbit. It looks much simpler than this one because we have taken all the constants out and calculated them. And Rn is just again n square, dependence on n square, 0.53 by z, and then it's in the unit angstroms. Okay, so these are very simple formulas to remember, and I don't want you to remember them really, but I want you to know the dependence is 1 by n square. That is very, very important. Okay, but does this model really predict something? We've calculated all the basic quantities, but does this model really predict something experimentally? Now, one thing that you can see experimentally is something called spectrum. Now, when an electron makes a transition from a certain orbit to a certain other orbit, you know that it emits a certain radiation. Okay, this electron which makes a transition and emits a certain radiation forms something called atomic emission spectrum. So the electron can be in E4 and come down to E1, or it might come down to E2, or it might come down to E3. Okay, and each of these will form a line. Okay, each of these will give you a particular characteristic frequency, and if you plot that frequency if you plot that line versus frequency, we'll see certain lines which happen at very, very specific points, very, very specific frequencies. Okay, so this is the atomic emission spectra, and we will see what it looks like. But before that, we have to calculate it. So the calculation comes like this. So this is the by now familiar form of the energy. So the electron in the nth orbit has this kind of an energy. Okay, we know that, minus 1 by n square into this constant. Good. And it makes a transition from orbit n1 to n2. Okay, so it was having an energy minus 1 by n1 square into this constant, and it comes to an orbit minus 1 by n2 square into this constant, the energy of that second orbit. So you just subtract the two energies, and when you subtract the two energies, by the way, this one we will do it in terms of wavelengths. So h nu was equal to these two energies, and nu is equal to c by lambda. So hc by lambda is just this. Okay, and we just subtract these two quantities. We just put n1 square once and n2 square once, and just subtract, and we get this hc by lambda is the difference between, so it's 1 by n2 square minus 1 by n square n1 square. It's a very simple little arithmetic. You can do it on your own, and remember this is the hydrogen atom, so Z is just 1, so remove Z, and just 1 by n2 square minus 1 by n1 square. Okay, what this implies is something very simple. You just take HC and take it to the other side, and you have 1 by lambda. So 1 by lambda is equal to this. So if you know 1 by lambda, you obviously know what lambda is, just the reciprocal. So you have 1 by lambda, and this is the constant. Okay, this is the expression that you get, where RH is a new constant. We just take all of this and make a constant out of it. That's called the Rydberg's constant. This whole thing is just a constant. So that whole thing is just 2 pi square e to the power 4 m by h square, which is just this part, and we saw that this was just 13.6 eV. Okay, so this was just 13.6 eV, so you can just plug this 13.6 eV over here, and then we have to calculate. We just have to calculate for different n1s and n2s. Okay, before we do that, let us note a couple of things. Okay, first, if you have different orbits, the electrons can be in the different orbits and it can jump to different orbits, and this transition gives you a spectrum. Okay, now every element has a different arrangement of these orbits, and this is a very important statement. So every element has a different arrangement of these orbits, and these orbits give you a different spectrum. Just by looking at how these lines are spaced, what these lines are, how these lines are spaced, what the number of lines, etc., you can definitely identify the element. This is the very art of spectroscopy. Okay, so the atomic spectrum is like a signature of an element. Okay, you have hydrogen, you have a particular signature. You have helium, you have a particular signature. Though the spectrum of helium won't be explained by the Bohr model, because the helium is has more than one electron. This is just for a one electron system. The spectrum of neon, it's very well known. Spectrum of sodium, they are very known. So all of these spectra are very well known. And if I'm giving you one element and you don't know which element that is, you just form the spectra of that element. Find the spectra of that element, and you just match it to spectra which are known, and you will find that it acts like a signature. Okay, so most elemental identification, in fact now even compound identification, comes from matching spectra. Matching spectra is an incredibly powerful technique. Okay, and this is the first time. This is not the first time that it was done, but this is the first time when theory and experiment, they converge onto the same thing. So let's just compare. After all that, let's just compare. So this is the formula we had. So we have electron n1, which is making a transition to the orbit n2. Okay, this has energy E of n1, this has energy E n2. Okay, now let's just say n1 is, I'll explain to you what Balmer series is. The n1 is 3, n2 is 2. Okay, so the electron just comes from E3 to E2. Okay. Then the wavelength of light that is emitted, if you calculate, it just comes out to be 656.1 nanometers, which is just red. Okay, now if it comes from one orbit higher, which is n4 to n2, so it jumps from E4 to E2, then the wavelength that is emitted is 486 nanometers, which is just blue. Okay, how about n1 equals to 5, so E5 to E2. E5 to E2 gives you 433 nanometers, which is violet, and E6 to E2 gives you something which is darker in violet, so 410 nanometers. Okay, and after that you can have 7 to 2, and it goes into the ultraviolet, so you can't see. These are the 4 lines which are part of the visible spectrum. There are no other lines which form the visible spectrum. So the hydrogen spectrum has been extremely well studied. Okay, and it turns out that the hydrogen spectrum can have many different lines, but except for these 4, everything else is in the ultraviolet and not visible. Okay, so this visible spectrum, n3 to n2, n4 to n2, n5 to n5 to n2, and sorry, E3 to E2, E4 to E2, E5 to E2, and E6 to E2. These four lines form what is known as the Balmer series. Okay, so this is the visible spectrum. This is called the Balmer series because somebody called Balmer studied it the first. And now this is of course the prediction from the model. Okay, these are just numbers which are got by replacing values here in this formula. Okay, this is just a prediction. Okay, I know that 656.1 nanometers is red. I know that 486 nanometers is blue, and so on and so forth. Let's just find out what hydrogen gives in experiments. So hydrogen gives these lines in the visible range. The first line is 656.3 nanometers. Okay, 656.3 nanometers corresponds almost exactly to 656.1 nanometers. It's almost exact. Okay, so this matches. We can treat this as a very good match. The second one is blue, 486.1 nanometers compared to 486.0 nanometers is a very good match again. This one line in violet, which is 433.9, which is 434 nanometers. 434 nanometers here, extremely good match. And the last one is 410.1 and bang on 410.1 nanometers, so it matches exactly. And these are your experiments. So the theoretical predictions match the experiments very, very, very well. This is a huge success for the Bohr model. The Bohr model, which had these very ad hoc prescriptions. Okay, these quantization rules coming from nowhere suddenly predict something, some very tangible things, which is like the spectrum, and you can calculate that, and you can find that it matches exactly with the experiments. Okay, wonderful success. Now, obviously, the answer as to why the Bohr model should work was not obvious. And people went on to say that the atom is not only semi-classical, that is semi-quantum rather, it's fully quantum. We can't have a mishmash of laws which are somewhat classical, somewhat quantum, and that's not very satisfactory. We should have laws which are purely quantum. The classical laws will fail. We will have laws which are purely quantum, and people set out to describe a formalism, a quantum mechanical formalism, and this took a couple of decades. In the upcoming lectures, we will delve into the quantum formalism as it stands now. We will not look at all the developments that happened because it took a long time. We will take a look at the quantum formalism as it stands now, and from the modern perspective, we will see what it tells us, and we will see that it's very counterintuitive, it's very abstract, but it works wonderfully well. Okay, many counterintuitive things in physics work wonderfully well. Quantum mechanics is one of them. All of this in the next week's lecture. Do not miss it. It's the beginning of quantum mechanics. Thank you, and see you then.